Namaskar. I welcome you all to the second lecture of Svādhyāya 1.2. As you all know that quotient topology can be best understood through examples. So in this lecture, we will be delving into some wonderful, creative and nice examples for quotient topology. Let's begin.
Okay. So this is lecture 2 on quotient topology on Svādhyāya 1.2. So today we'll be discussing a bunch of examples of the quotient spaces followed by some topological properties. So let's recall that if X is a topological space and if tilde is an equivalence relation defined on X, then if this is the set of all equivalence classes on X, and then we saw that there is a natural map from X to X tilde which sends X to its equivalence class. Okay, and this map is a surjective map also, and the space this we say as a quotient space. And now we define a topology on X mod tilde as you take any set U in this, and that is open if and only if the inverse image of U under pi is open in X. And with this topology, we say the quotient space as the quotient topology. Okay. So now this space, we have endowed a topology, and we saw that this is the largest topology so that this pi is continuous. Okay, and that was our requirement in order to define a topology. So recall that in order to define a topology, there were at least two requirements. The first one is that the quotient map to be continuous, and the second map, it has to be the largest topology on X mod tilde. And this topology satisfies both of these properties. Okay. So we also observed this theorem which says that if you have a continuous function between two topological spaces which preserves the equivalence class or equivalence relation, so that means that if two elements are related, then their image is same. Okay, so if it is so, then it induces a map on the quotient space to Y. So by that I mean, then there exists a continuous function g from x mod tilde to y such that f is equals to the g compose pi. So let us quickly see a proof of this. Last time we discussed, but we were in hurry. So let's quickly see a proof. So x to y, we have a map f. Okay, and now we also know x to x mod tilde, we have the quotient map. And the theorem says that if f is continuous and it preserves the equivalence relation, then I can find a map G such that this diagram commutes. So this means that G composition pi is equals to F. Okay. So what is the natural choice of this G map? So you see that if I'll go from the backward direction, so if I have here x, so this will go to f of x, and this is going to class of x by pi. So a natural choice of the map should be that the class of x should goes to f of x. So we should define that g of class of x is equals to f of x. Okay, so this is my definition. Now, since G is defined on an equivalence class, so we need to make sure that this is well defined. That is, if let's say equivalence class of X is same as equivalence class of Y, then I need to show that they mapped to the same point. Okay, so let's prove that. So if equivalence class of X is same as equivalence class of Y, this means that x is related to y. But this means by the assumption f preserves the equivalence relation. So this means f of x equals to f of y. But this is what? This is your g of x, and this is equals to g of y. Okay. So this proves that this function is well defined. Okay. Okay. By the choice that f of x equals to g compose pi x, this is also satisfied. Now I only need to show that g is a continuous function, and that is also not difficult to show. So let's make the diagram again. So x to x mod tilde and to y, I have a g. So what I will do, I'll take a open set here, u. Okay. I need to show that G inverse U is open in X mod tilde. So inverse U is open in X mod tilde, it means what? It means that if I take the pi inverse of G inverse U, that should be open in X. Okay, fine. But you need you observe that we have this property, f of x equals to g of pi of x. So this means that pi inverse of g inverse of u, which is nothing but g compose pi inverse of u. Okay, and note that this inverse is just set theoretical inverse here I am taking. This is not like the inverse function I am taking, because I don't know the maps are bijective or not. So this is just set theoretic inverse I am doing it here. So G compose pi inverse U, and what is this? This is by the definition, this is F inverse of U. Okay. And I know that U is open in Y and F is continuous. So this implies this is open in X. Okay. And this proves that G is a continuous function. So see, we got a very nice result that whenever we have a continuous function between two topological spaces X and Y, the only requirement that we want that the F should preserve the equivalence relation. If it is so, then that will induce a map on the quotient space. Okay. And this theorem will be helpful to, like, whatever we make the guesses in the previous session, that if you have a finite line segment and joining one point, like the two endpoints giving a circle, joining the boundary of a disk giving the sphere, and many more, we have a guess of a continuous function from the quotient space to the space that we were guessing. Okay, so let's see that. So let's discuss the first example. So I'm taking x to be the 0, 1. Okay, x is my 0, 1. I've already made the picture, so yeah. And now I'm defining the relation on x as x is equals to y or xy belongs to 0, 1. Okay. So this means that class of X, we have only two, we have like two types of class. One is equals to, it contains singleton X. Okay, and if X is does not belongs to 0, 1, and it is equals to 0, 1 if X belongs to 0. Okay, okay, fine. So with this relation, we want to see what is x mod tilde. We have already observed that this should be a circle. So now our guess or our aim is to prove that this quotient space is indeed a circle. Okay. So this is the thing. So this is my 0 and this is my 1, and here it's 0 and 1 are same. Okay, so this is our aim to show that this is indeed a circle. So now recall that our previous theorem, if this is my x and this is my y, okay, so I need to find a continuous map between x and y first of all. So let me write my aim. So find a continuous map f from 0, 1 to y such that f of 0 equals to f of 1. Okay, so this is my aim. And if this is true, then by the theorem, I know that there exists a G. So this, by the theorem, then there exists a G from the quotient space to S1. So S1 is the circle. Okay, and that's continuous. So our main job is over, that we got a continuous function from a quotient space to circle. Now we only need to show that that map is a homeomorphism, then we are done. Okay, so it means that we have to find a map like this. Okay, so let's observe here what's really this is doing. Like, so you saw that if I wrap around this point, and if I label some points on the line segment on the closed interval 0, 1, then what exactly is happening? It's wrapping here at some point. So it suggests that all these points I'll send to corresponding point on the circle, and these 2 points I'll send to this. Okay, and we already know a map from 0, 1 to S1 which has the above property. That's basically the parametrization of circle. So how will I write? A circle I can write with cosine x and sine x, where x is in 0 to 2 pi. Okay. But since we are in 0 to 1, so instead of taking x and cosine x, sine x, I'll define my map to be x goes to cosine 2 pi x and sine 2 pi x. Okay. Now this is my f. So we got a function f. And this is a continuous function. Why? Because each coordinate is a continuous function. So we recall that from our multivariable calculus, that if f equals to f1 dot 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 fn, then f is continuous if and only if each of the fi's are continuous. Since cosine and sine functions are continuous, so therefore f is continuous. Okay, so my first job is over partially, it's done. So now let's see what is the image of 0 and 1. So what is f of 0? That's 1, 0. And what is f of 1? That's again 1, 0. Okay. So this proves that f is a continuous map which preserves the equivalence relation. So therefore, by our theorem, we have this. So what we are getting is f a continuous map. So by the theorem, I'll be getting a map G. And what is G here? G of x will be equals to cosine 2 pi x and sine 2 pi x. Okay, this is my map. And G is continuous. Now, we also note that G is a bijective function. Okay. And why so? So we look at the picture, you see that if I'll take any point other than this, then any point this here corresponds to one point on the interval. And this, so it means that the pre-image of this has exactly 1. Okay. So the pre-image contains only 1 element. And now the only problem was this point. But if I'll take the pre-image here, it contains 2 points. But in the lower side, in the quotient, that contains only 1 point. So it means that for every point on the circle, I have a unique pre-image in the quotient space. And therefore, G is a bijective function. So I encourage you to discuss this fact. Okay. So we got a bijective function from x mod tilde to S1 such that G is a continuous function. Okay. So what I know, there is one thing that I know here. And what is that? See, one way to prove that this is a homeomorphism is to prove that this map is also continuous. Okay, the inverse map is continuous. One way to prove that, directly you show that the inverse map is continuous. And how to show that? So just I'll give you an idea. So I'll define the inverse in 2 ways. Okay, so this part I can write. So this part of the circle I can write x comma square root 1 minus x square, and this part I can write x comma minus of square root 1 minus x square. Okay, this is how we can write the circle. Now with this I can define a map, and with this also I can define a map. And now I have, like, so I partition the circle into A union B. Okay, and I have defined my H1 from A to x mod tilde and H2 from B to x mod tilde. Okay, right. And now you see that on this, like these are the points which are in the intersection, and on these points H1 and H2 matches. Okay, and therefore by the pasting lemma, that you know that if H is a map from, or HI is a map from AI to X, and such that HI matches on the intersection, then I can define H on the union of AIs. Okay, and that's a continuous map. So with this, I will define my H, which is equals to H1 and H2 depending on A and B. And since this H1 and H2 are matches on the intersection, this function is continuous function. Okay, and this will give you one way to find out the inverse, and one can show that this is indeed an inverse and the inverse, and hence the function is, and this is continuous, and hence this is a homeomorphism. So this is one way to show that. Okay, another way to show that, okay, so another way to show, so yeah, so right, so let me write down here. So we got 0 1 to 0 1 mod tilde and S1. Okay, and this is my pi. Okay, this is a compact set, and we know that a continuous image of a compact set is again a compact. So if f from x to y is a continuous function, then f of k is compact if k is compact. Okay, so this also you try to prove in the discussion. So it means that this is a compact set. Why? Because this pi is a surjective map. Pi is a surjective and continuous. The image is a S1 is Hausdorff. Okay. And why? Because any subspace of a Hausdorff space is again Hausdorff. So S1 is Hausdorff, and it's not difficult to prove these topological properties. So therefore, I have a continuous bijection between a compact set to a Hausdorff space. So I have a continuous map or a continuous bijection between a compact set to a Hausdorff set. And this implies that F is a homeomorphism. And we have already discussed a proof of this fact in the previous discussion. So just go through the proof. First, try the proof by yourself. Okay. So this proves that this is a homeomorphism. So we saw two methods to prove that the quotient space to circle is a homeomorphism. One way is to direct construct the pre-image or the inverse image, and the other way to use this very strong result that says that a continuous bijection between a compact set to a Hausdorff space is a homeomorphism. Okay, so this completes the example 1. A similar example. Now, instead of a closed interval 0, 1, what we are doing, we are like taking x as the whole R, the real line, and defining a relation like x mod tilde, x is related to y if and only if x minus y is an integer. Okay. And this, you need to prove that this is homeomorphic to S1. Okay. So just to give you a flavor, you see that we know that if we also know that R is a group. Okay. And we know that if I consider this, that R as a state and Z as a group, then Z acts on R. Okay. And R mod Z is precisely this quotient state, not as a topological, as a quotient group here I am telling. And this we know from our group theory that this is also circle as a group. Okay. So yeah, there are two things. So one, we are getting it as a quotient group is same as the circle, and the thing that we need to prove here that the quotient space is same as circle. So note that here we cannot use the result that from compact directly because R is not compact. So we cannot directly say that the image is compact. But a hint here is R mod Z is again a compact set. So try to see this, why it is compact. Okay. Yeah. Let's move to the next example, which we have discussed. So this is a construction of cylinder. So what I am doing, just take a square sheet, okay, and glue the opposite end. So I glued these two. Okay. I glued these two. And what I am getting is a cylinder. But that's like our guess that it should be a cylinder. Now we need a proof that the quotient space is indeed a cylinder. Okay. So again, what is our job? Our job is to find a continuous map between this square to the actual cylinder. So I'm writing at C. Okay. And now, and how do you define cylinder? So let me just write it down, the C as a set. So this is x, y, z, such that x square plus y square equals to 1, and z, since we are taking -1 to 1, so z varies between -1 to 1. Okay, so this is my cylinder. So again, the thing that we have to prove here, we have to find a continuous map between this square sheet to cylinder, which preserves the equivalence relation. That means this f should match it on these points. Okay, so f should match on these points. So it means that the value of f at this point should be equals to value at f at this point. Similarly, at this should be equals to this. Okay. So you see what exactly is happening. So if I take any line on the square sheet and if I wrap it, what I'm getting a circle here. And that's precisely the previous example that we discussed. So if I consider here in this, there are a bunch of lines here. Okay. And what are we doing? We are just taking each of the line and gluing to get a circle and stack it to get a cylinder. That is what precisely we are doing. Okay. So we have this kind of thing. So do we have a map? Yes, we have a map. So how do I define a map here? So I take any line. So this line, how do I describe? This line I can describe in two with the three parameters. One is x and y is of course there, and this height. Okay, this height will determine that which circle it maps to. Okay, so what I will be doing, I'll be sending this xy to the first two coordinates should be circle, so that's cosine 2 pi x and sine 2 pi y. And what would be the last coordinate? That's the height, that's this. So that's precisely y. Okay. So my function is xy maps to cosine 2 pi x and sine 2 pi y. That's maps to the circle. But which circle? So the circle which is y at a distance of y from the bottom. Okay, this is the map. And again, this map is continuous map. So let's write down. So f of xy is equals to cosine 2 pi x sine 2 pi x and y. And f, so what is this? F is continuous. And you note that you take any point, this point and this point, the function value are same. This point and this point, the function value are same because these two are matching. And why it fixed? Because we are taking at the same height. Okay. Similarly, at these 2 points, the function values are same. So f of x equals to f of y if x is related to y. Okay. And just to write down the class, so what is the class of 1, 0? What is the class of, let's say, if I'll write the class of -1 and 1, just try to write down these classes. Okay. So take some points to get a feeling of that if I'll take any point, let's say this point is my AB, then what is the class of AB? Okay, so just try to write it down. Okay, so we got a function from square sheet to cylinder. Okay, so again, and this function is a continuous function. So what we got? We got by the theorem that there is a continuous map from from the quotient space to cylinder. Okay, and again you see that this G is a bijection. Okay. And X is compact, therefore X naught tilde is compact, and this cylinder is a Hausdorff space, and therefore this is a homeomorphism. And this proves that the quotient of square on the opposite sides give you a cylinder. Okay. So good. We also like saw in the previous session that if I take the cylinder and now glue the two opposite circles, so if I'll take this and if I glue this to this, I'll be getting a torus. Okay, so I'll be getting a torus, something like this. So if I want to just highlight it, so one will be my this and one will be my green circle. Okay, so I'll be getting like that. So again, so how do we write torus? So torus we can write as the product of two circles. Okay, so torus is basically product of two circles. So we have a product topology here. Okay. If you don't know product topology, just assume that like we are here. We have just some topology with just like we are just multiplying two, taking two open sets and just like writing like for example, if you have R2 like R cross R, and how is the topology looks like? It's like this cross this. So therefore we have these kinds of open sets. Okay, so same picture is here. Okay. So now what do I want to show and what is the relation? So the relation is on the square sheet, I'm gluing these two as well as this. Okay. So this point is glued to this point and this point is glued to this point. Okay. So this means this is equivalent to this point and this is equivalent to this point. And therefore, you note that the corner points, all corner points are equivalent. So if I'll see what is in the equivalence class of this point, this contains 4 points. Okay. So there are 3 kinds of equivalence classes here. One contains 4 points, other contains 2 points, and remaining contains singleton points. Okay, so any point here inside contains singleton. Any point on this contains 2 points. Any points on this also contain 2 points in the equivalence class. Okay. So the picture is clear. Now, how do you define a map from these two torus? Okay, and the map is very clear because we have written torus as a product of circles. So this again, see, if you wrap this, I'll be getting one circle. If you wrap this, I'll be getting the other circle. So therefore, how do I define the map? So okay, these two torus, so I'll just write it down. This with this. Okay, so this kind of picture we'll be getting there. Okay. Okay. So how to define a map here? I'll take X and Y and send it to. So this green will go to the green circle. So I'll be getting cosine 2 pi x sine 2 pi x. Okay. And this cyan color will go to this, the bigger circle. Okay. So that is what will be cosine 2 pi y and sine 2 pi y. Okay, so this is the map. Again, this is a continuous map because each of the coordinate is continuous, and hence I'll be getting a continuous map between these two. Okay, and again, what is this? This is again a bijective function. Okay, and therefore this is a homeomorphism. Okay, so you see that this result is a very important result. So let's write the result. So maybe I'll discuss the examples. And so let's write this result that I was telling, that if X and Y are compact, assume further that Y is Hausdorff. Let f from x to y be a surjective continuous function. Okay, so note that in all the previous example, f was a surjective function. And now we define the equivalence relation by defining that. Now we are defining the equivalence relation by this point. Okay, so it means that our condition for quotient induced map in the quotient space is satisfied. And therefore, I do have a map between this and y. And since X is compact, this will be compact. Since Y is Hausdorff, this is Hausdorff. And hence, this is a homeomorphism. Okay. So we don't need to assume Y is compact, but that will again follow because X is compact and F is a continuous map. Okay. And and that's surjective also. Okay. So we don't need to assume Y to be compact. Okay. So this is a very important result and a very strong result in the quotient topology to see what is the quotient space, which space is the quotient space familiar to. Okay, so let's discuss one more example. So here the relation is not very straightforward that was there in the previous examples. So what exactly we are doing, we have X as the Euclidean space, two-dimensional Euclidean space, that's R2, and we define an equivalence relation on X at, so you take any 2 points, x1, y1 and x2, y2, and we are saying that these two are related if and only if this happens. The x1 plus y1 square equals to x2 plus y2 square. Okay, and we need to describe what is x mod tilde. Okay, so like when you watch this video, I suggest you to pause it here, try to think what is the equivalence classes here. Okay, so for example, what is an equivalence, what is the equivalence class of 1 0, what is the equivalence class of 0 1, what is the equivalence class of 1 1, or some points, and then arbitrary what is the equivalence class of AB. Okay, and then that equivalence class will determine what this space will be. Okay, so I encourage you to pause it here and think of that what will be the quotient space. Okay, so let's describe it. So if I have R2, this is my R2. So if I want to see what is an equivalence, what is the equivalence class of 1 0. So what is this? This will contains all such points xy such that x plus y square equals to 1 plus 0 square. That means 1. Okay. And what is this? This is a parabola that x equals to 1 minus y square. That's a parabola. So if I'll put y x equals to 0, I'll be getting y at plus minus 1. So that's like this parabola I'll be getting. Okay. So this is the equivalence class of 1 0. Okay. And you see that if I want to find out equivalence class of any element AB, then what is the equivalence class of any points AB? This is equals to set of all xy in R2 such that x plus y square equals to a plus b square. And this is some constant. So let's write C. So this is what? This is a parabola x equals to y square c minus y square. So I'll be getting a bunch of this. Okay. And the equivalence class of 0 will be 0. Okay. So x, sorry, not 0, it will be this one. Yeah. Okay. So what we are getting is, so each of the equivalence class is determined by this constant. Okay. This constant. Each of this equivalence class is determined by x plus, so any AB will be in a plus b square. Okay. So it suggests, this picture suggests that the equivalence, if I'll collect all the equivalence classes, that will be R. Okay. And that is indeed the case. So our claim is x mod tilde is R. Okay, that is my claim. So again, the same thing. What I will do, I will define a map from x to R2. Sorry, not x to R2, x to R. How will I define? I'll take xy and send it to x square, sorry, x plus y square. Okay, I'll just take xy and send it to x plus y square. Now, by this construction, you see that f preserves the equivalence relation. Okay, it means that if I have 2 points A, B, and C, D, then what is f of AB? That's A plus B square, and f of CD is C plus D square, but they are related, so these two are same. And hence, f preserves the equivalence relation. Okay, and therefore, I'll be getting a map G from x mod tilde to R. And what is that map? xy, the class of xy will go to x plus y square. Okay, I got a map. This is a continuous map. Okay, fine. Now, but here again, I cannot say this is compact Hausdorff because this is not compact. Okay, so this is not compact. So this time we cannot say that compact Hausdorff. So now this time we are forced to define a map from R to x mod tilde. So R2. So let's define in this way. So R2 x mod tilde. Here we have a map x. Okay. So I'll not define directly. I'll go through via R2. So if I'll take any points xy here, okay, see, like just think of, sorry, not xy, x. Any point x, see, what is like the equivalence class of this? This contains, what is this? This will the set of all x, or let me write a0, that will be making more sense. So a comma 0 will be xy such that x square plus y is equals to a square. Okay, so this is completely determined by this constant a. Okay, so if I'll take x, I'll just send it to x comma 0. Okay, and that will be going to the class of x comma 0. So I'll just say define h of x equals to the class of x comma 0. Okay, and one can check, or you should check here. So let me write in the discussion session. You should check the following thing. H is continuous. That's not difficult. The second thing is G compose H is equals to identity on R, and H compose G is equals to identity on X mod tilde. Okay, and with these two things, we can say that my quotient space is homeomorphic to R. Okay. Okay. So I hope this is clear to everyone. So let's go to one more example, and that is a similar example, but that I'll leave for you in the discussion session. So now instead of x plus y square, we are taking x square plus y square. Okay, so 2 points. Again, the same problem. Like the relation that we are changing, xy y1, x2 y2 is related if and only if squares are same. Okay. So what are the equivalence classes here? And what will be the space x mod tilde? Okay. Here note that these equivalence classes are determined by something. Okay. That's determined by the sum of the square. Okay. And that is always non-negative. This is always non-negative. Okay. So it means that given any r, I'll have some xy such that x square plus y square, given any r bigger than 0. I have some x and y such that x square plus y square. And therefore, a candidate of x mod tilde would be what? That is left as an discussion exercise. Okay. I've already told the answer here, but you have to figure it out where is the answer. And then you have to prove that that is indeed the case. Okay. So yeah, so this we have already discussed. So this completes a list of examples. There are plenty of examples you can by this technique you can produce a bunch of examples to see like how is the quotient space and all is doing well behaved. Okay. So yeah. So now we have already proved this thing we have already proved. So let's go to some of the topological properties that we have discussed. See, I was keep telling that if x is compact, then x mod tilde is compact. So yes, this is indeed the case that if x is compact, then x mod tilde is also compact. And why so? Because we have proved that. And the fact that we are using that if f is a continuous map between x and y, and if x is compact, then f of x is compact. And how do you prove this? So this is not difficult to prove. So let's quickly see the proof of this fact. So that's not difficult. So how do you prove that the sum set is compact? So I will take a open cover of that set. So I'll take, so this, I'll take an open cover. So take an open cover of f of x. Okay, so I'm naming it as V alpha such that alpha is in some index set. Okay, and each of the V alpha are open in Y. In tau Y. Okay, what do I have to show? That there exists a finite subcover. What I know, X is compact and F is a continuous map. So for each V alpha here, the inverse image F inverse V alpha is open. Why? Because F is a continuous map and V alpha is open. Named it as U alpha. So this U alpha, such that alpha belongs to I, this is an open cover of X. Why? Because V alpha was open cover of the image set. Okay. So that's why the inverse image will be the open cover of X. But X is compact. So this implies I'll be getting a finite subcover. There exists some UI1, UI2, UIN such that X can be covered in the union of UI1. Okay. So now what is an obvious choice? With each I1, I'll just take VI1, VI2 and VIN, and my claim should be that X mod tilde, or sorry, f of X is covered by these things. Okay. And this is not difficult to show. So this you can try to show. Now, here what is this now? So here X is X2 X mod tilde. This pi is a surjective map, and hence this is compact, therefore this is, sorry, since X is compact, therefore X mod tilde is also compact because pi is a surjective continuous. Okay, so this proves that if X is compact, then X mod tilde is also compact. This is one of the topological properties. I'll also discuss two more properties. It's connected and path connected. So again, the idea is same. If F is a map between two topological spaces X and Y, okay, and let's assume it's surjective. Otherwise, we'll just say the result for F of X. Okay, so if it is continuous and let's say X connected, then Y is also connected. Okay, and this is not very difficult. So if I have just, I'll make with pictures. So if this is my X and this is my Y, see, connected means it does not have a separation. That means Y cannot be written as the union of A union B, where A and B are proper subset of X and they are non-empty. Okay, so this we cannot write. So, but you see, of course, A and here I am assuming that A and B to be open. Okay, yeah, right. So, yeah. So see, if I can write Y as A union B, so Y equals to A union B, where A and B are open, A, B non-empty. Okay. Then what is this? F inverse of A is also open because it's a continuous map, and F inverse B is also open. But you see that Y, F inverse Y is what? That's X. And therefore F inverse A union B is X. And therefore F inverse A union F inverse B is equals to X. Okay. So you see, if one of them, so let's not assume non-empty, so that I don't want to go through the contradiction. I want to directly prove. Yeah. So if both were non-empty, then this has to be non-empty. Okay. But then X has a separation, which will say that X is disconnected. So it means that one has to be empty. Okay. So this means that F inverse A or F inverse B is empty set, and therefore A or B, one of them is empty, and therefore the other is X or Y. So we prove that if F is a map, a continuous map between two topological spaces, and X is connected, then the image is also connected. And same is true for the path connected. So if I have my X and if I have my Y, and F is a continuous map, I need to show that between any 2 points, there is a path. So Y1 and Y2. Okay, what I will do, I'll take in the pre-image, I'll just take some point. Okay, there may be many points in the pre-image, but I'll choose some point, let's say X1 and X2. Okay, I know this is path connected, so I'll be getting a gamma here. Okay. Now, how will I define this? See, this x1 and x2. So there, see, so since, so if I'll write with the quantifier, since f of y1 belongs to f of y, so there exists x1 in x such that f of x1 is equals to y1. Okay, this is. So I am telling there exists some x1. It may be there are lots of x which maps to y1. Okay, yeah. So this is my gamma. So gamma is a path between x1 and x2. Now how will I define a path between y1 and y2? Eta. So how will I define? Eta t. That's obvious choice. What I will do? I'll just do this thing. So I'll just take f of gamma t. So this is a continuous map. And what is eta 0? So if eta, let's say gamma is a path from 0, 1 to x, eta is also a path from 0, 1 to y. So what is eta 0? That's f of gamma 0. But what is f of gamma 0? That's y1. Because gamma 0 is x1. So that's y1. Similarly, eta 1 is equals to y2. And that will give you a path. So this proves that if x is path connected, then the image is path connected, and hence here x mod tilde is path connected. So I'm assuming, of course, surjective here also, and continuous. Okay. Yeah. So this proves you some topological properties of the quotient space. Okay. So now I leave you a bunch of problem sheet for you to discuss. There are already a lot to discuss, and these are 3 extra problems to discuss. The first one is, like, if you define an equivalence class on R by this, that x is equals to y equals to 0, or xy is either they are 0 or the product is bigger than 0. Okay. So how many elements are there in this, and write down all the open sets and all those things. Okay. And then the second one is that if x is discrete, then what would be the quotient topology? And the third one, it's something that we will be discussing in the next session. That's called real projective plane. So I've given you one construction, and we will be discussing more construction. And probably in the next discussion, we'll also discuss this, that a disk, if you take a disk and if you identify the whole boundary to one point, then I'll be getting a sphere. Okay. So this also we'll be discussing in the next class, and we'll explore some of the more quotient spaces which will be helpful in your general arbitrary topology structure. So okay. So yeah. So thank you. So